First of all, I'd like to thank main organizer of this meeting, especially Shahram Abati, for inviting me this meeting. I'm very honored. So I have been working on star formation for more than 30 years. Now we have some understanding to some extent. So today I'd like to explain our recent understanding of star formation process in our Milky Way galaxy. Okay, I'd like to show the pointer. Can you see my pointer? I think yes, right?
Yes, that's okay.
Okay, thank you. Okay, this is the outline of my talk. First, I'd like to give you some introduction, and I want to emphasize important 3 timescales, and I will explain some observation. Then I will talk about so-called phase transition dynamics of interstellar medium. This is about the formation of molecular cloud. Then I will talk about our recent paradigm of star formation. This is directly related to initial mass function or rotation of the core, rotation of the astronomical object, and protoplanetary disk. PP stands for protoplanetary disk. I don't think I have time to explain destruction or dispersal of molecular cloud and other issues. Okay. So time is limited. Let me move on. Okay. This is, I guess many of you know this plot. This is a very famous Kennicutt-Schmidt-Rowe plot. Okay, horizontal axis is a gas surface density, and the vertical axis is the star formation rate per area. Okay, we have some nice correlation according to the observation, mostly extragalactic observation. Okay, let's take some typical value of the horizontal axis, and then let's divide the value by the vertical axis. Then result is in a dimension of time, and the value is on the order of a giga year. Therefore, people working on galaxy tends to say that gas consumption timescale is about 1 giga year. Okay, this is the essential star formation timescale. Okay, 100% of all the gas transform the order with a timescale of giga year. Okay, but recently we have another plot. So many people are now using high density tracer because this gas include H1 gas and molecular class, okay, diffuse gas and dense gas. But now we are focusing on the dense gas. If we use a dense gas tracer, then actually this relation is more simple. Okay, again, horizontal axis is a mass. This is not a per area. This is just a mass of the dense gas. Vertical axis is star formation rate. Okay, now this is a linear relation. Therefore, if you divide horizontal axis by the vertical axis, then you will get same, which is on the order of 20 million years. Therefore, people say that gas transformation timescale of the dense gas is on the order of 20 million years. Of course, this value is a bit simplistic because this is transformation of the 100% of dense gas. In reality, star formation efficiency is not 100%. It's only a few percent of gas transformed into stars. Therefore, this time scale is actually a combination of the actual time scale and star formation efficiency. Okay, so this time scale is essentially a star formation time scale divided by efficiency. Okay, now let's compare these 2 time scales. Okay, there is a factor of 50 difference. Okay, 1 giga year and 20 million year, there's a factor 50 difference. This might be understood by the fact that fraction of dense gas is 1 over 50, say 2% of the total gas. Okay, that is a typical well, expectation. Okay, and this is now measured by observation. So if you are interested, please look at paper by Tori et al., for example, very recent paper. Okay, so in this way, we can understand the relation between these two time scales. Okay, I have explained this to 1 giga-year and 20 million year. But we have to understand basic time scale of the interstellar medium. That is a dynamical time scale. Okay, following the classical popular discussion, we can obtain actually 1 million year. Okay, let me explain briefly. Okay, we know that star formation explosion rate in a galaxy is 1 per 50 or 100 year. Okay, let's take 1 per time scale 100 year. Okay, within the expansion time 1 million year, supernova remnant expand to the big radius, very large radius, that is on the order of 100 parsec. Therefore, volume occupied by supernova remnant can be calculated in this way. This is in a steady state. Okay, this is a time scale. This is a rate and the time scale, and this is a volume occupied by 100 parsec cube. Okay, this results in a 10 to the 10 cubic parsec. Okay, this number actually accidentally same as the volume of the galactic thin disk. Look at this. 10 kiloparsec is a typical size of a galaxy, and 100 parsec is the thickness of the this galaxy, where we can find dense star-forming molecular cloud. Okay, this number actually same as this number. This means that okay, volume of the galactic thin disk are completely occupied by this bubble, which means that any region in a galactic thin disk are swept up by supernova remnant once per 1 million year. Therefore, we can say that basic dynamical time scale of interstellar medium is 1 million year. This is a shockwave sweeping time scale. This is much smaller than the rotation of the galaxy, which is about 200 million year. Okay, so this is about supernova remnant, supernova explosion, but of course, H2 region, expanding H2 region can be also important. But anyway, let's take the number 1 million year. This is a typical time scale of a shockwave sweeping. Okay, in order to understand all of these time scale and star formation, we have to understand formation of molecular cloud. Okay, let me move on to the formation of molecular cloud. Okay, first of all, I'd like to explain what is a radiative equilibrium phase. I'm not going to the detail of this plot, but this is actually various heating and cooling process. Okay, by equating heating and cooling process, we can obtain equilibrium temperature as a function of a given density. Okay, horizontal axis is the number density of the ISM, interstellar medium. The vertical axis is the equilibrium temperature. Okay, this branch is like a 10,000 Kelvin branch. This is about 100 Kelvin. This is about 10 Kelvin. Okay, and if we multiply temperature with density, we can obtain pressure. And the pressure shows this kind of funny shape. This is a decreasing function of density. So let's suppose ambient pressure is this red line. In this case, we have 3 equilibrium points. Okay, but in the middle, this middle point, actually pressure is a decreasing function of density. Therefore, this is thermally unstable. So this is thermally unstable. We have 2 thermally stable branch, and this is called warm neutral medium or warm medium, and this part is called cold neutral medium. Okay, we have two phases. 2 phase is in pressure balance. That is a basic concept of interstellar medium. Okay, dense part and low density part, or cold part and warm part. Okay, and we can assume that mass of the ISM are in both cold neutral medium, the warm neutral medium, but density difference is huge. It's more than 100. Difference with density more than 100. Therefore, most of the volume are occupied by warm neutral medium. Volume occupied by cold neutral medium is tiny, so tiny. We can safely assume that most of the volume in the galactic thin disk are occupied by warm neutral medium. Okay, then formation of cold neutral medium is essentially a phase transition because this density jump is very large. And this is done by nonlinear compression because linear perturbation or small perturbation cannot change this state to this state because both branches are thermally stable branch. So in order to transform low density warm neutral medium into cold neutral medium, we have to compress non-linearly. This is done by propagation of shock wave. And I hope this movie works. Oh, it's not working. I don't understand why. Sorry, this movie doesn't work. Sorry. Okay, this is actually a snapshot. Okay, after movie shows that shock propagation or shock wave are propagating upward. Okay, shock wave moving upward, and this region corresponds to the post-shock layer. Post-shock layer becomes turbulent, thermally unstable, and become turbulent. And this turbulent motion does not decay as long as shock wave propagate into warm neutral medium. Now this is a typical result. So in this way, we can by the red region correspond to the high density region, high density, low temperature region. Okay, so in this way, we can create by the blue part correspond to low density warm neutral medium. So please be careful. Actually, we are observing this process in a moving coordinate. Therefore, actual position is moving downward, but actual shock wave is propagating upward. Shock wave propagating upward. Okay, so in this way, propagation shock wave create cold neutral medium, but created cold neutral medium are always turbulent, very turbulent, and this picture is confirmed by many other people. This is a French group, and this is actually a Mexican group, and this is this is a German group, and this is a Mexican group. They all confirmed this picture. Okay, one of the important property of this process is actually spectrum. So we are now talking about highly compressible gas. Okay, density difference is more than 100, but actual spectrum follows Kolmogorov turbulent laws. Kolmogorov law. Okay, essentially a 5/3 Kolmogorov law. You might be surprised because we are talking about highly compressible gas. Why? Turbulence is famous for incompressible fluid, like water, turbulence in water, right? So reason is the following: because this turbulent motion is created by pressure in an interclamp medium, that is warm neutral medium, and this velocity is actually smaller than the sound because this is created by pressure of warm neutral medium. Therefore, this is actually a subsonic turbulence. This looks like a supersonic with respect to the sound speed of dense cold medium, but this is subsonic with respect to the interclamp medium. Therefore, actual scaling law follows incompressible like Kolmogorov turbulence. Okay, so let's move on. We have a nice understanding, but we're still missing one important physics. That is, of course, magnetic field. Okay, so Actually, I have to explain so many things about the magnetic field, but let me show you just the result. Okay, I will skip all the detail and I explain the result. Okay, main question is the following: can direct compression of magnetized warm neutral medium create molecular cloud or not? Okay, the answer is no. So the answer is very different from the case without magnetic field. Now we have a magnetic field. This is a snapshot of the compressed layer. This is compressed by left-hand shock wave propagating from the left-hand side, from the right-hand side. Okay, this is a two shock wave sandwiched compressed layer. Okay, if we don't have magnetic field, we can create high-density material, turbulent, almost molecular material at the center. But with magnetic field, we cannot create high-density material because magnetic pressure remains, and magnetic pressure support against this compressional motion. Okay, our calculation uses two fluid MHD simulation. Two fluid means neutral fluid and ionized component. So therefore, ambipolar diffusion is automatically included. But we found that ambipolar diffusion is not enough. It's not sufficient enough. Therefore, magnetic pressure remains at this compressed layer, and they will support against compressional motion. So therefore, we finally concluded that we cannot create molecular cloud from warm neutral medium by just one compression. And now this conclusion is confirmed by many other international groups. Okay? So in order to create molecular cloud, we need multiple compression, typically 10 times or 20 times compression. That is our result. So what is a typical result after many times of compression? And this is the result. This is the result. Okay. So this, you can see the filamental structure. Actually, this is I removed the black bar. Black bar corresponds to the magnetic field line. So I will show again black bar. Magnetic field line is like an oblique direction, and you can see massive filament that is perpendicular to this magnetic field lines. Okay, and I don't think you can see the striation, but actually if you look at here, you can see faint filamental structure, which is actually parallel to the magnetic field. Okay. Faint filaments are parallel to the magnetic field. The massive filaments are perpendicular to the magnetic field. Actually, this is agree, or this mimics the observation. This is a famous result by people working on Herschel telescope. Okay, their main finding is the following. Okay, star formation occurs always in a filament whose line mass is larger than critical line mass. Okay, critical line mass is written by this number and essentially determined by self-gravity because gravitational constant G appears. Cs is the sound speed. Okay, so if the line mass of filament exceeds critical line mass, then we expect star formation. That is a very simple summary of the Herschel telescope. Okay, now our theory can explain how this star forming massive filament can be created as a result of cloud formation process. Okay, in this way, we sometimes we say filament paradigm because star formation process understood in terms of filamentary molecular cloud. Okay, but you might ask, what about other mode of star formation? Some people say that cloud collision is important, and some people also say that expanding extrusion correct the dense gas and the collapse result in the star formation. Okay, this is a kind of a continuous star formation process by collect and collapse ask, okay, which is a more important star formation process? Okay, my answer is very unique. My answer to this question is that, okay, actually these three apparently different star formations paradigm or scenario are actually different aspects of one single unified theory. So these are actually all same. That is my answer to this question. Okay, let me move on. But before move on, I'd like to explain that, as I said, galactic thin disks are occupied by supernova remnant. Actually, this small square circle corresponds to the identified supernova remnant in this region by Roland Anderson. Okay, I'm not going to the detail, but now I like to emphasize that our galactic thin disks are occupied by many bubbles. Okay, then our picture of cloud formation is the following. Okay, this circle corresponds to the surface of a bubble, and the surface of bubble are occupied by turbulent H1 and cold neutral medium is turbulently moving inside of warm neutral medium. Only in some limited region we can observe formation of molecular cloud. Okay, only in a limited region we can observe, because this region corresponds to a special place where material experienced many times of compression, or compression is along the magnetic field line. Okay, so in this way, molecular clouds are created in some limited region of bubble, but the whole bubble are covered by turbulent H1 cloud. Okay, and because the expanding velocity corresponds to on the order of 10 km per second, so therefore velocity dispersion, or cloud to cloud velocity dispersion should be on this order. Okay, and we can expect star formation start even in this faint molecular cloud. Once the line mass per length of the filament is exceed the critical line mass. Look at this. In this region, maybe these two clouds may collide in the future. In this case, we can create huge amount of dense gas, which may result in a cluster formation. Some of the massive star forming region mimic can be observed like this, and this looks like a combination of a filament, many filament. Okay, this is expected because each cloud should have this kind of filament structure. Collision of these two clouds create this kind of messy filamentary structure. So in this way, our scenario also explains massive star formation. So I think I don't have time, so I have to move on fast. So our integrated scenario include massive star formation and cluster formation as a cloud-cloud collision scenario. And also, our scenario is essentially consistent with the collect and collapse scenario. But also, our scenario also explain many other property, but today I don't have time. I just, in the remaining time, I just briefly explain these two aspects. By the way, how many minutes I can talk from now?
In principle, you have about 5 to 10 minutes. Depends on how you can wrap it up.
Okay.
How many slides do you have left?
I think I have many slides, but okay, I will spend, say, 5 minutes. Is that okay?
Yeah, that will be good, and that gives you time for some questions.
Okay. Thank you very much. Okay, let me move again. I briefly explain two important aspects. I think this is interesting to you. Okay, so this is a observed core mass function. Horizontal axis is the mass of the core. Vertical axis is a histogram. Okay, this observed molecular cloud core mass function mimics stellar initial mass function. If the mass of the 30% of core becomes star, then we can explain stellar initial mass function. Now, understanding stellar initial mass function is to understanding the core mass function. This core mass function can be essentially explained by fragmentation process of like this, right? So, but this can be actually, I have a problem. Okay, and I think it's this number. I will explain this way. Okay, and actually I have a prediction I had many years ago, and okay, let's measure the mass distribution along this z-axis, and let's take the Fourier transform of the mass distribution. Now my prediction is that if this power spectrum follow this kind of value, then we can explain the salpeter mass function. And indeed, observationally, mass spectrum along the filament are now observed to follow k to the n. N is minus 1.6. In this way, and this 1.6 actually close to Kolmogorov 5/3. So observationally, we know that mass distribution along the filament is follow 1D Kolmogorov, and if this spectrum follow 1D Kolmogorov-like spectrum, then we can explain salpeter-like core mass function. So in this way, we can explain from the filament paradigm, we can explain the core mass function. Okay, and this is actually a theoretical result predicted like 18 years ago. Okay, let me move on. Okay, final topic. What about rotation? Okay, we know that sun is rotating. Rotation period is about 1 month. Sun is rotating. All the other stars are rotating, and that is the reason why, after the death of a massive star, we can create rapidly rotating neutron star. Okay, and even for the black hole, we know we are now detecting gravitational wave from the binary black hole. Why we have binary? Because they have angular momentum. Why they have angular momentum? Because they have the angular momentum from the beginning as a star formation process. And the moment this newborn star, that should be understood in terms of the angular momentum of molecular cloud core, right? So let's try to understand the origin of angular momentum of molecular cloud. Okay, so let's move on. Okay, this way, in principle, okay, we have already explained the core mass function or mass histogram of the core from the fragmentation of filamentary cloud. But this should also explain angular momentum. Suppose that we have this kind of velocity fluctuation, velocity component, then this should result in a rotation of core like this. So rotation of core should be determined by initial condition. So we have to explain the rotation of the core as using the property of initial condition. We studied this, and actually calculation is very easy. We just as a function of mass of core, because angular momentum is a conserved quantity. Okay, angular momentum should be conserved. So therefore, we just calculate the conserved quantity, angular momentum. And I think I have to move on. This is the observation, but I skipped this, and this is the result. Okay. Again, okay, blue line corresponds to 1D Kolmogorov spectrum of the velocity fluctuation. And just on reference, I plot this red line. This corresponds to 3D Kolmogorov, 11/3. Okay, 3D Kolmogorov doesn't work. By the way, this black point corresponds to the real observation, actual observation. Okay, in order to explain this black point, I think we should have exponent something like this. Okay. Again, Kolmogorov spectrum fit very well and explain actual observed angular momentum of molecular cloud core. Okay. Actually, I have the explanation why we have 1D spectrum, but I skipped this and put this summary slide, and I just mentioned that according to our recent unified picture of star formation, we can explain many things. And Kolmogorov turbulent law is very important, and we can explain the cloud-to-cloud velocity dispersion. And I skipped this, but I can explain acceleration of star formation. I also skip these things, but if you're interested, please look at this paper. And I leave this slide and I stop here. Thank you very much.
Thank you very much. That was a very interesting presentation and very nicely done. It's now time for our audience to raise hands for questions, if there is any. I'm trying to check the public chat to see if there are any questions.
Habib, may I ask a question?
Yes, please, go ahead.
Sorry, I cannot raise my hand because I'm connected with my mobile, so.
Okay, no problem. Go ahead.
Yeah, thank you very much for the nice talk. My question is about the effect of the gas expulsion of the early gas expulsion of star clusters in the formation of thin disk, thick disk, and I mean at least for Milky Way disk. Is it? I didn't understand how much this effect is considered in your formulation, your method.
Okay, you're asking about the thick disk component of galaxy. Is that correct?
Yes. Yes. Exactly.
Okay. That's a good question. Actually, we don't know how to create. No, actually, many people are providing many theory about the formation of thick disk component of our Milky Way galaxy. So actually, I'm not expert on that. But today, what I explained here is only applicable to the thin disk component. Thin disk means that scale height is, say, less than 100 parsec from the midplane. So star formation still continuing